Good morning. Welcome to the 24th lecture on economics, management and entrepreneurship. In our last lecture, we were discussing various methods of comparing economic alternatives. We will continue the discussion on those topics today. To start with, let us recall that we had fundamentally three methods of comparing among economic alternatives. One was the present worth cost comparison method, where we discount all future cash flows to the present. The second method was equivalent annual cost comparison method, where we try to find out the annuity, the equivalent annuity of each of the proposals. And in the third method, we try to find out the internal rate of return method. Present worth cost comparison method is applicable when the number of interest periods is the same for all the alternatives. Otherwise, one has to apply either repeatability condition or coterminous condition to apply present worth cost comparison method. And when the lives are different, the number of interest periods is different for the projects, then the equivalent annual cost comparison method is the best. But if there is only one project and the decision has to be taken as to whether the project is a worthwhile proposition economically or not, then we compute the internal rate of return method and then compare the value of internal rate of return with the minimum attractive rate of return required by the company. If the internal rate of return is higher than the minimum attractive rate of return, then that project is considered worthwhile. Now, internal rate of return, if you recall, is basically the rate of return at which the present worth of all cash flows becomes 0. So, we had in the last class taken one example to show how to compute internal rate of return. Now, internal rate of return can be visually seen in this interpretation can be made of internal rate of return. Assume that we have made an investment P initially and that over the life of the project of n years there are different expenses and there are different revenues. So, the meaning of the word internal in the internal rate of return is that this amount is reinvested at the IRR, which is R here. So, if P is reinvested, its equivalent amount at the end of 1 year is P into 1 plus R, and then at the end of year 1 the net revenue is R 1 minus E 1. By that amount the amount is reduced. So, the unrecovered investment balance is P into 1 plus R minus R 1 minus E 1, that means it drops to this. Again it is assumed that it is reinvested for 1 year and then again the net revenue is subtracted. Like that this continues till at this point of time it becomes equal to 0. The value of R that results in the unrecovered investment balance to be equal to 0 is called the internal rate of return. Basically, it means that the amount that is unrecovered investment balance is reinvested at a rate of internal rate of return. So, this is a difficulty with IRR, that actually it is not reinvested, and in particular if let us say the value of IRR is very high, of the order of 50%, whereas the MARR is just about 15 or 20%, then it is never imaginable that a particular amount is invested internally at 50% rate of return. So, this is not practical. This is a problem with internal rate of return. The second problem, we of course know that computation of IRR is difficult, because it involves a method of trial and error using the values of the factors from the interest tables. There is yet a third difficulty, and that it is possible to have more than one values of rate of return at which the present worth of all cash flows may become equal to 0. That means, there can be multiple values of internal rate of return, and when there are multiple values, interpretation of the multiple values is difficult, as also the calculations may not be correct. We are not discussing these aspects of multiple values of IRR, but the fact is that solving for IRR may result in more number of values of IRR, and one is not sure which one is the correct value. So, because of these reasons, IRR is sometimes not preferred, but it is quite often cited in the industry for comparison with MARR to find out whether a particular value of a particular project will be accepted. This is what we have written here, the difficulty with reinvestment decision of IRR and the problem of multiple values of R. These are two problems for which one goes for what is known as external rate of return. It considers the rate of interest epsilon external to the project, at which the net cash flows generated or received by the project over its life can be reinvested. Now, this we are showing in the form of another diagram here. Here, as before, this is the initial investment P and the expenses over the years E1 through En, and revenues over the years R1 through Rn. What is first of all done is that all expenses are discounted to the present at the external reinvestment rate of return, which is normally equal to the MARR. So, if epsilon is the external reinvestment rate of return, meaning MARR, then all these E1, E2, E3 etc. are discounted to the present. So, that is what we have written, discounted to the present. So, first of all they are all discounted to the end and then discounted to the present. That is what is done here. This is each EI is discounted to the present. So, each is considered as an F. So, E1 to the multiplication P given F EI, that is single payment present worth factor is multiplied with E1 plus E2 into single payment present worth factor, that is multiplied with I equal to 2 here, like that, and then this whole amount which is considered the present is taken to the find out the compound amount here. So, F given P comma R comma N. So, this is the final sum of total discounted expenses computed at external rate of return R. So, this should be equal to, there is a one mistake here, this should be P plus, because P plus and then yes. So, all these are discounted to the present, plus there was a initial investment P. So, that is the total investment made by the company, and that is then found out, the equivalence is found out at the end of the nth year. So, multiplication, the single payment compound amount factor f given P r n. So, r is taken here, whereas the discounting was made at the rate of MARR. We are interested to find out the external rate of return r. So, if this amount was invested externally, then we are calling it P r n, and that is equal to all the revenues when their final sum is calculated at the end. The final sum is R I multiplied by find f given each one as P. So, P epsilon n minus 1. So, each one, the final sum is found out at this point, and all expenses plus the initial investment calculated here are the final sum is found out at this point, and they are made equal. So, in this case, since epsilon is known, the value of MARR is known, we are therefore, we can find out the value of f given P r n, and therefore, r can be determined. So, here we are not making any trial and error consideration. So, basically what we are doing, all expenses we are discounting to the present, adding to that the initial investment made, that is now the present sum. The final sum is calculated by finding out or multiplying that with the compound amount factor, and then equating the whole thing with the compound amount of all the revenues throughout the year. By that process, we find out the external rate of return. Often this external rate of return is used instead of internal rate of return, and then the same method of comparison is made. ERR is compared with MARR. If ERR is higher than MARR, the project is considered economically viable, and if external rate of return ERR is less than MARR, then the project is considered not viable. So, this is an alternative to the very popular internal rate of return method. Now, we introduce yet another method called capitalized worth method or CW method. Now, in the capitalized worth method, we assume that an equal payment or receipt is made for a very large number of years, particularly let us say the government projects which are very long duration projects, a dam, a bridge, a road, and similar such projects which require large investment and which has a very long life. For this purpose, we can use a simple formula. What we can do? We can assume that all our receipts or expenses are equal and continue up to infinity. That is what we have done here. So, cash flows are assumed to continue for an infinite length of time. And so, suppose this is the cash flow and this continues up to infinity, then we know that this is like A. We assume the annuity A per year to be constant, and suppose we find out the present worth of these cash flows. So, to find out P given A, equal payment series present worth factor, given A, find P, multiply that with A will give us the present worth of this cash flows. And if it was n, then the formula is 1 plus r to the power n minus 1 divided by r into 1 plus r to the power n. Now, if n tends to infinity, it can be shown that this is equal to a divided by r. This quantity is 1 upon r. 1 upon r can be taken out, and this is 1 minus 1 divided by this, n tending to infinity, this quantity becomes 0. So, this becomes 1 by r. Therefore, this is a into 1 by r is equal to a by r. So, this is a much simpler formula to use. So, suppose for example, a is 100, r is 0.1, then the capitalized worth is equal to 100 by 0.1, which is 1000. This is the meaning. We give here a more realistic example. The company is interested to set up an advanced manufacturing laboratory, for which it invests 1 million rupees. So, this is the initial investment made. This is a cash flow diagram. It is estimated that the lab requires an annual expenses of rupees 300,000 and an amount of rupees 200,000 at the end of every 4th year. So, 300,000 rupees annual expense for the laboratory, this is the operating expense, and this is at the end of every 4th year there is some maintenance expense. So, here there is an expense, here also there is an expense, and 12th year there is another expense of 200,000, whereas 300,000 rupees per year is continued throughout for every year. Now, this continues for a very long time. We are assuming that long to be infinity, and therefore, we can straight away use the capitalized worth method, meaning we can find out the present worth of this. The present worth of this is, first of all, this is taken as minus, because it is a cash outflow, minus 1 million rupees, and then for this quantity it is 300,000 plus, if for each one of these we find out the annuity, then that means we consider this as 200,000 and the equivalent amount we can now find out. This is 4, 3, 2, 1. So, the equivalent of this 200,000, the equivalent annuity for this 200,000 will be given by 200,000 multiplication A given F R 4. This is the sinking fund factor, equal payment series sinking fund factor. So, that is A given F, R is equal to 0.08, 4. So, this is the equivalent annuity of a payment 200,000. So, similarly, for this amount, this will also be 200,000 multiplication A given F 0.084. So, we will, because of this there is another annuity here, because of this there is another annuity here, and therefore, we can actually add them. That is what we have done here. This originally was 300,000, and because of this it is 200,000 into this. So, this is therefore, the equivalent annuity considering both the cash flows, and according to our capitalized worth method, this is the A divided by R is 0.08, that is 8% rate of return is given. So, that makes it this minus this, once again there is a mistake here, this has to be minus. This is minus 5,300,000. 304,750 rupees. This is the capitalized worth. If we have a similar project or another project with different cash flows, we can separately find out its capitalized worth, compare the two, and since both are cost, the one that gives the lower cost is what is accepted. Now, so we have now up to now we have discussed in fact 5 methods: the present worth cost comparison method, the equivalent annual cost comparison method, internal rate of return method, external rate of return method, and now we discussed about capitalized worth cost comparison method. Now, all these methods consider time value of money. Now, traditionally however, in industries people use or rather do not use the time value of money so much. What they do is a thumb rule, that is called the payback period. And of course, a variation of payback period is discounted payback period method. So, these are the traditional methods, particularly the payback period is the most traditional and is very much used as a thumb rule to decide whether a project is worthwhile to make investment. So, payback or payout period method and discounted payback or payout period method. Now, payback or payout period method is basically finding out a time period theta by which the initial investment is fully realized. That means, if I have invested 10,000 rupees, in the first year I may be getting back 4,000, in the second year I may be getting back 3,000, in the third year I might be getting back 4,000. So, totaling 4 plus 3 plus 4 makes it 11,000. That means, by the third year I have fully realized my initial investment of 10,000. So, payback period is little less than 3 years. This is how the payback period is calculated, and in the symbolic form it is given in this fashion: RI minus EI, revenue minus expenses for every year, summed over I equal to 1 to theta minus the initial investment I should be greater than or equal to 0. As you can see, this method does not consider the time value of money. A project with a payback period of less than 3 years is usually favored, because the company who has invested an amount of I is getting back his money in cash form or in some form in 3 years time. The net revenue is 3 years. If it is so, then that project is considered good. This is very popular in industries. However, this method considers only liquidity rather than profitability, because it does not consider the entire cash flow. Hence, a rejected project may be more profitable in the long run. This I can explain in this manner. Let us say that a project is paying back its money in 3 years time. Another project paid back its or can pay back its money in 5 years time. So, naturally this first project is preferred, because it takes less time to get back the investment, initial investment. But we have really not considered the future cash flows. It can happen that the second project gives very high profits in the 5th year, 6th year, 7th year and 8th year, and the first one does not give so much profit. Therefore, if the entire cash flow is taken, maybe the first project is not economically better than the second project. However, since all the future cash flows beyond 3 or 4 years have not been considered, project 1 or the first project has been considered better. Therefore, this is a problem with the payback period or payout period method. to take care of the time value of money, sometimes discounted payback period is calculated. So, here what is done, this is a concrete example. So, what is done, that the net revenue minus expense, the net income is the present value is found out. So, that is considered as a final sum. The present value is calculated, that means the single payment present worth factor is multiplied with the income, and that is subtracted from I, and over a period of theta, this should be greater than or equal to 0 to find out the value of theta. Now, this is shown here. Let us say that initial investment is 25,000 and the net cash flow for the project for 5 years is, let us say, 8,000, 8,000, 8,000, 8,000 and 13,000. Now, considering only the payback period, initial investment was 25,000 and we get back 8,000. Therefore, 17,000 remains unrealized after the end of the first year. After the end of the second year, 17,000 minus 8,000, it is 9,000. After third year, it is minus 1,000. Only in the fourth year, it becomes positive. Therefore, theta is equal to 4. So, this is the payback period. Now, when we calculate the discounted payback period, what is done, that 8,000 its present worth is calculated. So, at a MARR of 10%, the present worth is 8,000 divided by 1 plus R. So, that comes to 6.667. So, what remains unrealized is 25,000, which was the initial investment, minus the present worth of the income after the first year. So, unrealized amount is 25,000 minus this, which is minus 18,000. After the second year, similarly, this 8,000 is discounted to the present, meaning 2 years, year is taken as 2. That means, 8,000 divided by 1 plus R, which is 10% square. So, that amount is lower than this, it comes to 5,556, and therefore, the remaining amount is this minus this, which is 12,777, and similar calculations are now made for the after the third year. The present worth is 4,630. If you subtract this amount from here, you get the unrealized amount of 8,147, and after the end of the fourth year, it is still negative. Only in the fifth year, it becomes 934, it becomes positive. Therefore, the whole amount of initial investment is realized only after the fifth year or only in the fifth year, and therefore, theta is equal to 5. So, you can see that in the payback period, where we do not consider time value of money, the payback period is 4, and in the discounted payback period, it is 5. However, the fact remains that the future cash flows are not considered in either of these methods. So, these are traditional methods, and therefore, they are quite popular, however, but they do not have the fundamental basis of consideration of time value of money, and therefore, one should not depend on, or one should not take conclusions or base conclusions on the basis of the payback period or even the discounted payback period. Now, in practice, there are some issues concerned with varying interest rates. This is one example of interest rates that vary over time. Here, suppose that an investment is made or a payment is made for 1000 rupees, it is quite possible that in the first year the interest rate is 10%, in the second year the interest rate is 12%, in the third year the interest rate is 15%. So, this is an example of interest rates varying with time. So, if I calculate the final sum here, the compounded amount of this payment at the end of the first year, then it will be F1 is equal to 1000 into 1 plus R1, which is basically this. The final sum F, this factor is single payment compound amount factor. To find F given P at the value of R1 as equal to, there is one mistake, there is no need to write here R, because already we have given the value of R. Similarly, here so R1 is 10% and this value can be obtained from the interest table. Otherwise, we know that it is nothing but 1 divided by 1 plus 0.1, which is 1.1. So, that not divided by, multiplication. So, this multiplied by 1.1 is nothing but 1100. Then suppose we are interested to find out F2, then taking this as the principal, we can find out its compound amount, which is 1100 multiplication for 1 year, it is 1.12. So, that comes to 1232, and here it is compounded at the interest rate of R3 equal to 15%. Therefore, it is 1232 multiplication 1.15, and that comes to 1457 rupees. So, in general, if we are interested to find out the equivalent final sum Fn, it is P multiplication product of 1 plus R1 into 1 plus R2 into 1 plus R3 written in this manner. Or equivalently, if we are interested to find out P given a final value, then its discounted value can be found out in this manner. So, when interest rates vary, then we can use these formulae. Now, another interesting case is the case of semi-annual interest compounding. We have so long considered interest rates that are defined for a particular year, although we said that it is particular period, but we almost implicitly assumed that one period is equivalent to 1 year. Quite often interests are compounded more frequently than once in a year. In this particular example, we are considering interest rates that are compounded twice in a year. That means, the time period at which or for which the interest is compounded is half a year. So, it is a case of semi-annual compounding. So, this is the cash flow diagram for such a situation. This is year, this is 1 year, first end of first year, end of second year, end of third year, and this is half the year, this is 1.5 year, this is 2.5 year. So, time period if you write, it will be 0, 1, 2, 3, 4, 5 and 6. So, in terms of years these are what is written here is in terms of years, but if I write in terms of time period, then it will be 0, 1, 2, 3, 4, 5, 6, etc. For example, this should be in terms of years, this is 1, 2, 3, but in terms of periods, I would write this is 0, 1, 2, 3, 4, 5 and 6 interest periods. This is what I am trying to say, that if it is semi-annual and if we are dealing with a problem of 3 years, then it is a matter of 6 interest periods. 6 interest periods. Now, we now define, suppose that the interest rate is defined for a full year, we call that as the nominal interest rate, that is not the actual interest rate. A nominal interest rate is defined for the full year, that is R. But if the interest is compounded semi-annually, that means after every 6 months it is compounded, in this case the interest period is therefore half the year and the interest is compounded twice a year. The interest rate for this half year is nothing but R by 2. So, if R is the nominal interest rate for the full year, for that interest period, one interest period, it is R by 2. Therefore, the compounded amount F at the end of the first interest period, meaning at the end of 6 months, half the year, is equal to P multiplication 1 plus R by 2, because R by 2 is the interest rate given for this half the year. And then for the full year, it will be this amount F 1.5, that is F calculated at this point, will be compounded here. So, this is F half, which is nothing but P into 1 plus R by 2 multiplication. For this amount it is compounded, it is 1 plus R by 2. So, this quantity becomes P into 1 plus R by 2 whole square. So, if it is compounded semi-annually, at the end of the year it is not P into 1 plus R, but it is P into 1 plus R by 2 whole square. There is a difference. So, what is the equivalent interest rate, which we say effective interest rate? Let that be RE. So, in this way, where we are calculating compounding twice a year, the amount comes to P multiplication 1 plus R by 2 whole square. Whereas, the effective interest rate, suppose it is RE, then it would be equal to P into 1 plus RE. Therefore, this 1 plus RE will be equal to 1 plus R by 2 whole square. That is what we have written here. 1 plus RE is equal to 1 plus R by 2 whole square. That now defines RE as equal to 1 plus R by 2 whole square minus 1. So, you can see that this RE is greater than R. The effective interest rate per year is higher than R, and we can show it with an example such as this here. Let us say that an amount is compounded at a nominal interest rate of 12% per annum, at a nominal interest rate of 12% per annum. So, that is the R. So, it can be compounded semi-annually and it can be compounded every quarter, meaning 4 times a year. So, we are required to find out the effective interest rate RE in each case. So, I am defining a quantity M. Just one second. Actually, what I am trying to say is that if an amount is compounded M times in a particular year, and suppose that R is the nominal interest rate, and M is the number of compounding number of times amount interest is compounded in a year, and if R is the RE is the effective interest rate, then RE will be equal to 1 plus R by M to the power M minus 1. Compare that this formula with this, it is RE is equal to 1 plus R by 2 square minus 1, and when the number of times the interest is compounded is capital M, then this 2 will be replaced by M and the power, the exponent will be also replaced by M. So, this becomes 1 plus R by M to the power M minus 1. So, when suppose that it is semi-annual compounding, M is equal to 2, R is defined as 12%. Therefore, it is 1 plus 0.12 by 2 whole square minus 1, and this quantity is obtained as 0.1236, which is 12.36% per year. So, although the nominal rate is 12%, when it is compounded semi-annually, the effective interest rate is higher at 12.36% per year. When instead the interest rate is compounded 4 times a year, then M is equal to 4. So, this becomes effective interest rate then becomes 1 plus R by 4 whole to the power 4 minus 1, and that is equal to 1 plus 0.12 divided by 4 to the power 4 minus 1. This quantity is 0.1255, which is 12.55% per year. Now, you can compare this, the higher the frequency of compounding of interest, the higher is the effective interest rate. This is even higher than this. Therefore, the idea given here is that if the interest rates are compounded more than once in a year, the effective interest rate also rises. Now, if we carry this idea to the extreme and say that compounding takes place continuously, then what is the effective interest rate? Now, this is quite interesting. This is also quite practical. In practice, it is not that the rates are given only at the end of the year. It actually it gets invested, reinvested, and the interest rates are compounded almost instantaneously. So, in that case, how to calculate the effective interest rates, how to calculate the equivalent present worth final sum values. This we can now extrapolate our previous idea in this fashion. Here we are considering that there are m number of interest periods per year. So, if this is 1 year and every interest period is 1 by m, 2 by m by m becomes 1, m number of compounding of interest. So, the effective interest rate is R E equals 1 plus R divided by m to the power m minus 1. Now, if we assume continuous compounding, it means that m, the number of times the interest is compounded, can go to infinity. Now, let m by r be given as p, be defined as p. This r by m, we are saying m by r. So, what happens to this quantity? 1 plus r by m to the power m minus 1, that is R e, limit m tends to infinity is therefore equal to, if m tends to infinity, then p also tends to infinity if p is defined in this fashion. So, I can write p tends to infinity and this is 1 remains 1, r by m I now write as 1 by p, just the inverse of m by r is r by m, therefore, it is 1 by p, and the exponent m is nothing but r p. So, it is r p. Now, this quantity is nothing but e to the power r. This is a series. If we expand this for different values of p, then we will see that it is nothing but e to the power r. The first term is 1 plus 1 by 1 to the power r. The second term is 1 plus 1 by 2 to the power 2 r, 1 plus 1 by 3 to the power 3 r, and this will come as e to the power r. So, this quantity becomes equal to e to the power r because of this reason. Hence, R e, the effective interest rate, is therefore equal to e to the power r minus 1, or 1 plus R e is equal to e to the power r. Hence, if we are considering a present investment of p, and if the interest is compounded continuously, at the end of the year the value then becomes p into e to the power r, and if there are n time periods, it becomes p into e to the power r n. So, this is the expression for continuous compounding and discrete cash flow case. Now, we will discuss a very interesting case of cash flows that increase in a uniform gradient manner or with a uniform gradient. Look at this. We are now considering a cash flow. At the end of the second year, I am assuming that there is a cash outflow of the amount g. At the end of the third year, I am assuming it is 2 g. At the end of the fourth year, it is 3 g, and like this continues up to the nth year. Now, I can find the equivalent amount at the end of the nth year. this amount I can find out in this manner. I can assume this 2g as equal to g plus an extra g, this 3g as equal to g plus still another g, and like this I can continue up to this. Hence, I can consider all the g's. This is a equal payment series of value g. This is another amount of another equal payment series of g. This is yet another. This is yet another, and lastly this. So, I can find out the equivalent amount at the end here. For this, it is g multiplied by 1 plus r to the power n minus 1 by r. For this, it is n minus 2. For the third one, it is etcetera, etcetera. It continues. So, this can be summed and the value can be found to be a simpler one, and that can be given a notation g given f g r n instead of f given a r n. We stop here at this moment, and we will take up in our next lecture the consideration of inflation rate, and also we shall start a new topic on depreciation. Thank you very much.